All right, now we start. This is the fourth session. It's actually 343rd session of Tesos and Wi-Fi, but the fourth one that is part of this free class that Wireless LAN Professionals bringing to you. This is a Wi-Fi design class. We're going to be designing Wi-Fi with Ekahau, with Tesos, with Hamina, with WLANPros. I'm going to be covering all the tools that we have available in the market right now. And we're going to be, we're going to get to that point later, but hey, right now we're just learning how Wi-Fi works. If we don't know how it works, how are we going to design Wi-Fi? We don't know how it works. How are we going to troubleshoot these networks? So, hey, it's Saturday. Today is May 16th. This is going to be the fourth class. We have been talking about regulatory domains, entities like the IEEE and the Wi-Fi Alliance that are in charge of making Wi-Fi happen worldwide. So the guys, Wi-Fi Alliance also has a really tough task of, dealing with regulation. I know a regulator is another entity, but the Wi-Fi Alliance, they're always lobbying and trying to get things approved and passed and trying to get more spectrum and trying to help out with the whole ecosystem of Wi-Fi stuff. So we have been talking about waves. Good morning, Mark. Where are you at located? Look, you're early up as well. I know it's Saturday. Sorry, guys, but this is how we roll.
Texas, get some good Wi-Fi in before we mow the yard, right?
Yeah, there we go, yeah. You're 1 hour ahead of me. See, these guys from Russia and stuff, they've been up for a long time. They're like ready to go to bed. Not us, man. We're just waking up. These guys are from the future.
Can't say about the rest of the world, but today in Moscow is splendid weather, so I don't expect a lot of people from Russia and from Moscow.
Yes. What time is it there?
It's what, 5 p.m.? 5 in the afternoon? 5 or 6?
It's 3 p.m. in Moscow.
Is what?
3 p.m.
3 p.m. Oh, okay, it's early. All right, yeah, if you have a beautiful weather.
Midday and beautiful weather.
Oh, yeah, people are going to be outside. That's good. Enjoy the weather. The best part, this class, not only free, but it's recorded. It's going to be uploaded, and then you can watch it later. So that's great. All right, well, continuing with how Wi-Fi works, because we've been talking about waves. That's what APs are sending and receiving. That's what clients are sending and receiving. It doesn't matter if it's a phone, a tablet, a computer, a Chromebook, a sensor, whatever it is, it's waves. So we talked the last sessions about characteristics of these waves that a NIC, that's what we saw in the very last session, is how is it that a NIC works? Well, they have to they send and receive these waves, and then they process them and get the ones and zeros out of them. We're going to talk about modulations later and stuff, but then Wi-Fi works this way. A device in Wi-Fi, a NIC, for it to send waves, it has to go through this contention process. It has to go through this mechanism that allows devices to not send waves at the same time. In Wi-Fi, we're using the air as the medium, and those waves are going in the air. Well, since in the air is not data, it doesn't have any IP addresses, it doesn't have any MAC addresses, and in the air is not Anton or Mark or Ned. In the air is just waves. Then only one device in a frequency gets to send waves at a time. Because what happens if Anton and Evgeny, oh man, you're going to have to tell me how you say your name.
Evgeny. Женя.
Holy smokes. Okay, let's try again.
You can spell it like
Eugene.
Eugene in English, yes.
Eugene,
yeah.
Eugene, okay. No, say it again in English. I mean in Russian.
In Russian is Evgeny. In English is Eugene.
Evgeny.
Yeah.
Evgeny, close enough, Evgeny? Yeah, here we go. Eugene. Evgeny, here we go. So if Eugene send waves and Anton send waves at the same time, when I receive those waves, I don't know who said what. I won't be able to process those waves to get the ones and zeros because they're both coming at the same time from different places. So that's what's called a collision. I mean, it's not that those waves crash and collide and fall off the sky. No, it's a term that describes when waves from one device and waves from another device kind of like, cause interference or collide, and then I don't understand who said what because I have to get clean air, clean waves for me to get the ones and zeros out of them and make sense of it. So how is it then that Wi-Fi operates? Well, actually, you know what? Wi-Fi is very, 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 very simple. Only one device talks at a time. It's like in a conversation here. How many people in a conversation like the one we're having right now can talk at a time? Well, one person at a time. Because if two of you talk at the same time, like when Anton and Eugene were telling us about the time in Moscow now, I couldn't understand. Because one said this, I was like, whoa, what is it? One at a time. So we stop, and then you repeat, you retry, and you had to say the time was, because you happen to not be coordinated, and both said what time it was at the same time. Only one person talks at a time. Now, what is the protocol for us in this meeting that we're having right now? If you have something to say, Eugene, what's the protocol? You wait, right? You raise your hand, I stop, and then it's your turn. How is it going?
I try to speak, listen about other speaks. If I listen sometimes, I stop.
And then if someone else is talking, then you don't talk.
Yeah.
And then if you have something to say, then you get my attention, then I stop, and then you talk. Only one person talks at a time, and it's my turn, and it's your turn, and it's Ned's turn, and it's Tendra's turn, and it's Yuri's turn, and then it's Mark's turn, and then we all take in turns. Only one person talks at a time. It's pretty simple, right? Okay. Wi-Fi works like that. Only one device transmits at a time. Yes, down the road, we're going to talk about Wi-Fi 6 and AX, and we're going to see how multiple devices can transmit at the same time. But just for sake of simplicity and to try to explain this from the scratch, and we start building up on top of everything, in Wi-Fi, in a frequency, in a channel, one device transmits waves at a time. And it's also half-duplex. Half-duplex means I can either send waves or receive waves. I cannot send and receive waves at the same time. Like when we talk, we're talking and listening at the same time. Not, or Ethernet, it's full duplex. You can send on some wires and receive on other wires, right? You're sending and receiving at the same time. Not in Wi-Fi. In Wi-Fi, you're either sending waves or receiving waves, half duplex. Okay. So how then in Wi-Fi do I know when it's my turn to send waves? Because here we can raise our hand, interrupt, like, hey, Fernet, see, then I stop and then, yeah, what? Then we can see each other. Well, not the ones that have the cameras off, but I can raise my hand and then I stop and then it's your turn. Wi-Fi devices cannot see. Wi-Fi devices cannot raise hands. They don't have hands. So how do they know when it's each device turns to talk? Well, let me share my screen again. And that is what contention is. That's what we're going to be covering today in this session. We're going to be learning how is it that devices in Wi-Fi take turns. politely. Wi-Fi is a very polite protocol. I only send waves when nobody else is sending waves. I'll be respectful. If Anton is sending waves, I'll stop. I'll wait. And anything else that is in my channel, I will not send waves on top of them or try to be louder or scream louder than the others. Very polite. Anton, how do you say polite in Russian?
Вежливость.
Man, why do I keep asking? I'm like, wow, man, this is so hard. Okay, say it again.
Вежливость.
Oh, man. A verse, yeah, polite. Okay.
It's
If you know
quite
what that means,
simply to
very
pronounce. It's
yeah.
quite simply to pronounce
Is it
complicated
really?
words.
Okay.
If you just divide it like A fiatlă кюдль, it's simply
All right.
just divide it.
Okay. Maybe if you write it, it's probably going to be more.
Вежливость. It's like 3 different frames.
Okay. Like 3 different frames. I love it. See, this guy is speaking our language, man. 3 different frames. I like it. Okay, so how is it that we get to send a frame in Wi-Fi? So contention is this process in which Wi-Fi devices are going to be able to send waves, avoiding sending waves at the same time as other guys. So there is something called distributed coordination function. Funny thing is not distributed and it's not coordinated, but it's called distributed coordination function. In Ethernet, we have something called carrier sense, multiple access, collision detection. Saur put rather equivalent to CMA. I think you missed the S, or you missed the letter CS. Yeah, CSMA, CD, collision detection. Carrier sense means that's the mechanism for Ethernet. Carrier sense, I have to sense the medium, the carrier, because multiple devices have access to that medium. See, on an Ethernet network, multiple people are connected to the same wired network. So carrier sense multiple access. Before you send your electrical pulses on the wire in an Ethernet transmission, you have to sense the medium and see if somebody else is using it, because multiple devices have access to the medium. That's carrier sense multiple access. Same in Wi-Fi. In Wi-Fi, we sense the carrier, sense the medium, to make sure nobody else is using it, because multiple devices have access to a medium. Now in Ethernet, since it's full duplex and I can hear and I can receive and send at the same time, if I hear something I didn't say, then that means somebody else is using it. Or if I say, if I put 5 volts and I sense 10 volts, like, whoa, I didn't put this voltage on the wire, I can sense it, there's a collision, so I will detect the collision and back off. Like in a conversation. If I'm going to say something, you're going to say something like, oh, sorry, no, you go ahead. And then we stop. And then, buddies, what's happening? It's in party mode. Look at him. He's got like a festive background. He's got music, vodka. What's going on?
No vodka there, but this is a different laptop and it has just virtual background. That's all.
All right. Just waiting clowns to see walking on the back, like,
Well, actually, this is all to pay a favor for you, to you, actually. So we have a class on Wednesday, and Evgeny just poked me in the Telegram. Hey, you're missing your classes. Sorry.
You're getting an attendance fail here.
Yeah, yesterday I poked Evgeny to attend the session, so today he paid me back.
Oh, good. There it is. So in Ethernet, we detect collisions because it's full duplex. I can listen and talk at the same time. It's full duplex. So I detect collision. And if I detect a collision, I'll just back off, wait a random time, and then try again. In Wi-Fi, it's half duplex. So I cannot listen, receive waves, and send waves at the same time. So I cannot detect collisions. If I'm sending waves, I'm not listening to waves. So if I'm sending, I'm not receiving. And if I'm receiving waves, I'm not sending. It's half duplex. So I cannot detect collisions. I try to avoid them. Avoiding collisions is what we do in Wi-Fi. That's why it's collision avoidance, not collision detection. We cannot detect collisions. We can avoid them. So contention is basically that process, that mechanism built into Wi-Fi so that devices avoid sending waves at the same time as other devices. Does that make sense? Pretty straightforward. It's like a conversation, like what we humans do. Just that, sometimes we just yell louder, and, when we're in an argument with somebody, then we try to talk on top of them, and I was right, and you were right. We just try to go. That's not how Wi-Fi is very polite. If somebody else is talking, I stop. So we have to do what's a clear channel assessment. Before I can send my waves, I have to make sure that the channel is clear. I have to assess. I have to evaluate the channel and see if it's free. So since Wi-Fi devices cannot see, and cannot see if somebody's got the hand up, then what do? They hear. The first mechanism, it's called the physical clear channel assessment. The devices will physically listen, and one sub-mechanism right there of the physical is that I will physically detect preambles. Like other devices, the preamble. Remember the preamble? Up to that point, I haven't said anything, but that's the preamble where I'm like making a noise, in this case, sending some waves, letting people know that, hey, I'm going to say something. That's preamble detect, PD, or signal detect, SD. And right here, SD. Or in some document, they show this as, I think it's CS, channel carrier sense, CS. Carrier sense, CS. But preamble detect, signal detect, collision, carrier sense, either one of those three means that the device is physically listening to see if somebody else is talking, if somebody else is sending waves. If I can detect waves and I can hear them at -82 dBms or stronger, and some documents show this as -85, and some documents show this as -86, meaning if I can hear some Wi-Fi waves at -82 or stronger, that means the medium is busy. So I don't talk, I don't send waves, because evidently somebody else is sending waves. That is the preamble detect mechanism, the physical clear channel assessment. I detect signals from other Wi-Fi devices. Okay. There is another physical clear channel assessment mechanism. It's called the energy detect mechanism. If I detect energy in that channel, if I'm on channel 36 and I need to send waves, I will listen and see if somebody else in channel 36 is sending waves. And if I hear them at -82 or stronger, then medium is busy. I will stop. I will defer. I will respect their turn. It's their turn. They're sending waves. Now, what if it's energy, something that is not modulated the Wi-Fi way? I don't know, maybe a microwave oven. I'm in 2.4 and there's a microwave oven going on. And it's 2.4 waves, but they're not modulated the Wi-Fi way. But the energy is so loud and so strong, I sense the medium and it's like, whoa, if there is energy at -62 or stronger, I'll stop. I'm not going to say anything. Then I will not send my waves if the medium is busy. Don't worry, once we get to the spectrum analysis portion, we're going to go through some of this stuff, but this is how Wi-Fi works. One device sends waves at a time. And how do I know it's my turn? Well, there is the distributed coordination function, DCF. This is a process in which devices listen before they talk. So I will physically listen and I will physically detect energy. And if I either hear somebody else sending waves or if I detect energy that is too strong, I will stop. Questions up to this point? Okay, pretty straightforward. Next, there is a virtual clear channel assessment. Virtual. How does this work? It is tied to something called Network Allocation Vector, or the duration. In every frame, yesterday, the last class, we talked about the format of these frames on Ethernet, the format of these frames in Wi-Fi, and we talked about the preamble, the header, we talked about the payload and FCS and cyclic redundancy checks. If you haven't seen that session, watch it. Not right now, we're in class, later, okay? Watch that prior session later. So in the header, there's gonna be a field called the duration field. That duration field basically says for how long I'm gonna be using the meeting. So if I'm sending a frame to Anton, in the header is gonna be a field called duration. It says, hey, I'm gonna be talking to Anton for 320 microseconds. Then Anton is like, oh, okay, what you got? Then you stay up to receive the waves I'm gonna send you. Eugene, Boris, Mark, and the rest of the crowd here in class listen that and say like, oh, Fernay is going to talk to Anton. Fernay is going to send waves to Anton for 320 microseconds. So what you guys are going to do, you're going to set a timer, 320 microseconds. And you go to sleep. You literally go into power save mode. You go to sleep. Why? Because only one device sends waves at a time. Me, it's my turn. And if you're Anton, you stay up like, okay, what do you got? Because I said it's for you. Then you stay up to receive the waves I'm going to send you. But the rest of you guys go to sleep for 320 microseconds. Why would you stay up cycling at 5 billion cycles per second or 2.4 billion cycles per second when you're not going to be sending or receiving waves? So you go into power save mode to save battery, right? Now, Boris, you have something to say. You from upper layer, you say, hey, send this frame, this packet, this chunk of data. And then you say, oh, I got this data to send. Then you're going to check your timer, your nav, and then this thing starts counting down. 320 microseconds, 319, 300. Of course, we're talking microseconds. I'm just slowing things down here, putting in slow motion. 317, 300. And then when Boris, when you get this frame to send on the Wi-Fi, you look at your timer and there's like, oh, there's still 100 microseconds left of the 320 that Fernay said was going to be talking. So if nav is not equals to 0, what does that mean? That the medium's busy. Virtually, oh, there's still 199, yep, medium's still busy. So if nav, if the network allocation vector is not 0, that means the medium's busy. This is a second mechanism that we have in Wi-Fi to prevent devices from sending waves at the same time. This is the collision avoidance mechanism, distributed coordination function. Then, when it counts down to 0 and nobody else is talking, and there's no energy in the channel, then that means, oh, medium's available now. I can send my waves. Not yet. There are two more mechanisms that we're going to be talking about here in a second. So questions up to this point. Okay. There is also something called interframe space. That's the space in between frames. Kind of like the pause we leave in between words. Which is say really fast, but then there's different types. And we don't have to get into these details because there are short interference spaces and distributed coordination function interference spaces. And there are RIFs, reduced interference spaces, and there are point coordination function interference spaces. And who cares? There's a whole bunch of those. We don't control those. That's in the protocol. But an interframe space, yeah, we're going to see some of those later. Don't worry. But it's just a period of quiet time. It can be 9 microseconds. It can be 20 microseconds, depending on what's going on. It can be, it's just short periods of quiet time that you have to wait. Then there is the big one, the random backoff. We call this the game. Mr. Keith Parsons, since the beginning of his career in Wi-Fi, started putting all this complicated stuff into easy things to understand. So this random backoff procedure is called the game. And when we did live classes that we went and had it, I had a set of dice that I carried with me. I actually have them right here. I thought I saw it. Hang on one second. Right there. Here we go. Dice, see? It's gambling time, Eugene, look at that. And we played it in class. We'll just give, got 4 guys up here on the front and had them read from a magazine, gave him a line, but then I gave every guy one of these guys, a dice, see? And then everybody rolled the dice, boom. And then random backoff is a random number that you'll pull before you talk. So let's just talk about the game right now. This random backoff is a process in which a device will pull a random number and then start counting down until it gets to 0. And when it gets to 0, then it's your turn. So let's say I get Anton, Eugene, and Boris up here to the front of the desk, and then I show you a magazine that you all have to read. But since you cannot read all at the same time, how am I going to spread you so you talk at different times? I give you all one set of dice. Well, one die. Say one die. Hi, Mark. You're the English speaker here. Correct my poor Spanish. Is it one dice or one die and multiple dice? Is it one dice?
Sorry, I'm an engineer, not an English major.
As far as I remember, it's called snake eyes.
Snake dice?
Snake eyes.
Snake eyes.
Yes.
Okay.
Like 2 dice with ones, it calls snake eyes.
Snake eyes. Okay. So if I give you one, let's say, here, I'll play for you, Anton. I roll the dice, and then you get a 5. Okay?
Okay.
Boris, I roll your dice, and you got a 4. Eugene, let's see how lucky you are. You got a 4. Okay? So here's how it works. If we're going to play the game, you guys now have to walk away from the table as many steps as you got on your dice. Anton, you got to keep track of your number. What did you get?
5.
Boris and Eugene, 4. Okay, so 1, 2, 3, 4, and 5. I'm 5 steps away. Eugene, Boris, you're 4 steps away from the table. So I will count to 9. Okay? Well, 1, 2, 3, 4, 5, 6, 9, and then I clap. That's a counter. That's a time slot. And then you guys move 1 step closer to the table. So, Anton, you're now 4 steps from the table. Before you were 5 steps away from the table. Now you're 4 steps from the table. Boris, Eugene, you are 3 steps away from the table. Another time slot, I go 1, 2, 3, 4, 5, 6, 9. Everybody moves 1 step closer to a table. Boris, you're the 2. Anton?
3.
You're a 3. Another one was a 9. Boom. Boom. You 2 are 1 step away from the table. And then I count again, 1, 2, 3, 4, 5, 9, clap, and then everybody moves closer. Now, you 2 are at 0. Whoever gets to touch the magazine and read first, it's your turn. So let's say, Boris, you touch first and you read the first line. Today is a beautiful day in Russia. Now you have to read another line. Okay? Now, Eugene, sorry, man, you were too slow. You missed it. When you were going to talk, Boris was already talking. So since you have to read a line, it's not that you're like, oh, when Boris is done, I go like, no. Eugene, you now roll 2 dice. Okay? You got 9. 1, 2, 3, 4, 5, 9 steps away from the table. Okay? Boris, you were at the table, you read your line, you have to read the second line. What do you have to do? You roll 1 dice. Okay? 2. 2 steps away from the table. Anton, you're still at 1. So Anton, you're at 1 step from the table. Boris, you're at 2 steps from the table. Eugene, sorry, man, your luck's not very good today. You're at 9 steps from the table. Okay? Count to 9. 1, 2, 3, 9. Boom! Anton, 1 step closer to the table. You're at 0. It's your turn. Now, what do? You read your line. I'm going to go have steak. You have to read another line. What do, Anton? You roll the dice. Got a 3. 1, 2, 3. Boris, where are you at? At 0. Are you? Thought you got a 2. Come on, man, get with the program. Didn't you get a 2? Didn't you get a 2?
It was 1. No?
No, I think you got a 2. So when I clap and Anton was at 1, he got to his turn and you counted
Okay,
down to 1.
yeah.
Okay, come on, guys. All right. Now, Eugene, where are you at now? Every time I clap, you move 1 step closer to the table, so you're down to 8. Anton, you got a 3, right? The next turn. So you're over
It's
here.
my turn to, yeah.
Yeah, now I clap. Now, Boris, you were closer. Now you're at 0. Now it's Boris' turn. You read a line. Anton, you're down to 2. And then Eugene, you're down to 7. Okay.
And I roll the dice.
And then now, Boris, you read. I'm going to roll Boris' dice. You got a 5. Then you're here. Eugene, you're at 8, right? Or 7. Then
6.
see how it goes? Now I clap again, and then you keep going. And then it's like these guys keep talking, and Eugene, you're still coming down the line. Okay. If Eugene gets to 2 and happens then Anton is at 2, and then we go to 1, and then we get to 0, and Anton speaks faster than Eugene. Now, Eugene, since this is your 3rd time trying, I'm going to roll 3 dice for you. You got 6, 6, 2. You got a 14. Now you have to go 14 steps away, and you haven't been able to send your waves because these guys keep winning. I know it sounds stupid, huh? I'm never going to get to talk. Yeah. That's when Eugene is going to be calling tech support. Yeah, my Wi-Fi is really slow, man. Why? Because you keep trying to send data. Why can't you send data? Maybe you're too far away from the access point. Maybe you're sending data in a very congested environment. And then there are many people in the same channel, maybe many people getting numbers out. And then that's what's making Wi-Fi slow. Since only one device sends waves at a time, this random backoff is the game, as you can see. Of course, access points, they have no dice. And if you shake an access point, it's not like blah, 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 blah. That's not the dice in there. It's just there's something wrong. There's a loose screw or something. But that is what's happening. So before a device, before a NIC can send waves in Wi-Fi, it has to do a physical clear channel assessment and make sure nobody else is sending waves. It has to make sure that there is no energy in the channel. It has to wait an IFS. It has to pull a random number. And then it starts counting down to 0. And when all of those conditions meet, it's your turn. And this is done frame per frame per frame. You have to send a frame. You have to listen before you talk. You have to make sure nobody else is talking. There's no energy in the channel. You have to make sure nav is equals to 0. You have to wait your ifs. You have to play the game. And when all of those conditions meet, it's your turn. Boris.
Yeah, it seems that it would be nicer for a reader of the slide if after the random backoff, we have a physical layer assessment as well, because this is the way I detect that I'm the second one to talk. So when the random backoff goes to 0, then you need to sense the media. You just don't start.
But you have to play the random backoff again, because let me just give you an example. Many years ago, well, actually, let me just tell you that story in a little bit when we get to this, because here's what's going to happen. If station 1 is going to send data, the duration, let's say, is set to 60 microseconds. It calculates how long it's going to take to send the data. It adds the SIFS, a short interframe space like 9 microseconds, and then it calculates also how long it's going to take the access points to send an ACK. Remember, the acknowledgement say, hey, I got it, it's good. So it knows how long it's going to take the entire thing, and it says, I need to reserve the time for 60 microseconds. And then the other station, it knows it's going to take him 90 microseconds to send data. It calculates how long it's going to take to send the data, the SIFS, and of course, there is more. There's the preambles, and if there's CTS, RTS, CTS, all that stuff. It's basically calculating how long it's going to take me for sending this data, and it reserves the time. That's in the duration field. Okay? This is the interframe space stuff. And then the random backoff is when you get then devices sending, and then each time slot, each contention window is going to be 6 slots of 9 microseconds each. And then if the random number that station 1 pulls off, it's 54 microseconds in these 6 time slots. It's counting down, and each one I clapped, that's the 9 that I was counting to. 9 microseconds clap, then you move 1 step closer, 1 microsecond down, then you move 1 step closer. And then the device, I mean, this is not something we control. This is in the driver. This is each device pulling a random number. Maybe, as we saw with the dice, maybe you pull a 1. Oh, you're right here. Maybe you pull a 9. You're back there. And you talked, and then you roll the dice again, and then you got a 2. Like, okay, I'm right here again. And you're still at 8, but hey, I keep rolling a small number. Then what happened many years ago is that, because this is how it works. This is not actually a dice from a number from 1 through 6. It's a random number. The first time you go to send data, it's going to be a number from 0 through 15. 0 through 15 time slots. Okay. Yeah, you can pull a 15. Maybe you pull a 1 or a 2 or a 6. It is random. How do you say random in Russian? Here we go again, Mark. I don't learn, man. Random. I'm just hoping for that easy word.
Случайный. It's not that easy, though.
Yeah, no shit. Okay, so watch this. You pull a number from 0 through 15. Okay? Maybe it's 15, maybe it's a 1. And then you start counting down time slots. Then when you get to 0, and all of those, I mean, I'm just talking about the random backoff, the game, because there are other mechanisms. Preamble detect, energy detect, nav, IFS. Now we're talking just about this random backoff. Then let's say you get a 14, and then same process. Go down to 14, 13, 15, 10. I know you may say, oh man, but this is microsecond. I know. And for us, that may be, it sounds like a long time, but these guys are counting everything in nanoseconds. Microseconds, it's really fast. It's really fast. So you get to 0, you pull the SIFS plus this time slots, and then you get to 0, you send your data. If you fail, like Eugene did because Anton was faster, or Boris was faster, I don't know, you, Boris, and Anton, I think were the ones, Eugene never got to talk. So if you have to retry, the next time it's not going to be 2 dice, it's going to be a larger contention window. It's going to be a number from 0 through 31. And then if you get to 0, or let's say you send your waves, okay, and you got no ACK. What does that mean? That means that, I don't know, maybe they didn't receive my waves, or they received them and sent me an ACK and I didn't receive it because when the ACK was coming, Mark sent his waves at the same time and then I couldn't receive it. So I assume the intended recipient didn't get him, so I retry. Now, let me back off a little bit because I exaggerated a little bit the process. Eugene, if you get to 0 and you're going to send your data, okay, but your signal detect mechanism detected that somebody else was using the medium, then you defer, you wait. And then next time you still have your 0, or you're right there. You're going to go through the other mechanism, make sure that nobody else is talking. Like, oh, I got a 0, I'm going. If you send your waves and you don't get an ACK, that's when you pull 2. And now if you send your waves again and still don't get an ACK, now you're going to get a time slot from 0 to 63. And if you fail again, you have to retry, and then you got to get a number from 0 to 127. And then again, from 0 to 255. These are retries, okay? You have to retry to send the data. And then you go to a number from 0 to 511, and then a 0 to 1023 microseconds, 1,023. So you may say like, man, that's microsecond. That's like the blink of an eye. But for devices that are calculating everything in nanoseconds, this is a long time and too many retries. So this is inefficient. This is like, why do I have to go through? Because that is how Wi-Fi works. It's like when you go, now, why a larger number? So since only one device can talk at a time, let's say in channel 36, you have one access point, and that access point has 20 clients connected, phones, computers, okay? So how many devices talk? How many devices send waves at a time in channel 36? 1. It's that simple, okay? So those 21 devices, if they all need to send data at the same time, they all go through it. I'm going to listen, make sure nobody else is talking, make sure there's no energy in the channel. I will make sure the nav has counted down to 0. I'll wait my ifs, and everybody plays the game. So you pull a number from 0 through 15. There's 21 devices. Chances that multiple devices are going to get the same number are higher, aren't they? Because you have more people, more devices than you have numbers. So if 3 of you get the same number, when you're counting down and you get to 0, yeah, chances that 3 are going to send waves at the same time, there's going to be a collision and the 3 of you are going to fail and have to retry are high. So the next time you have to try, you're going to get a larger number. Now, if there's 21 of you and you're pulling numbers from 0 to 31, the chances are that you're going to get a different number than the other devices. This is why, my friends, having way too many devices in the same channel is a bad idea. okay? Because only one sends waves at a time. It's like when you go to the post office. I don't know if you have to queue, get in lines to, I don't know, buy food or go to a theater or go to a bathroom, you know, only one person gets in, they give you numbers. You go to the post office, you know, on Christmas, well, before Christmas, if you're sending something in Christmas, it's not going to make it there in Christmas. So let's say you go to a post office and there's 100 people. How do they prevent 100 people from going all to the front desk at the same time? Well, they give people numbers at the door. And you get a number, and you get a number, and everybody gets a number. And then somebody at the register, you know, 17, register 1. Then, you know, whoever's got 17, only one person goes to the register, one person at a time. That's how they distribute people in time so they don't all go to a register at the same time. This is how Wi-Fi works. Does this make sense? Okay, so I know, sounds inefficient, but that's how Wi-Fi works. This is why we spend time doing this, because not all technologies access the medium the same way. If you have a wireless camera and you're sending video, the camera is programmed to send 30 frames per second. And I'm not going to wait. I'm not going to listen. I'm not going to I send 30 frames per second. Oh, it's 60, higher resolution, 60 frames per second. And they're going to send 60 frames per second. And I'm not going to wait. I'm not going to listen. I'm just going to send 60 frames per second. That's what I'm programmed to do. Anton.
Vernier, does this arbitration mechanism work the same with the Wi-Fi and non-Wi-Fi traffic?
If it's non-Wi-Fi, then I'm going to rely on the energy detect mechanism. Here, let me go back here.
But still you play the game. That was the question, I guess.
No, because if there is non-Wi-Fi traffic, let's say there is Bluetooth traffic, okay? It accesses the medium in a different way. It has different channel widths. It frequency hops. It goes in different channels. So how is Wi-Fi going to do? Well, that's the energy detect mechanism. But here's the problem. When we talk about interference, was it in this class? I think so. Yeah, when we talk about waves and yeah, we'll talk about interference anyway. But remember, most of the interference in Wi-Fi comes from Wi-Fi. Did I mention that before? Most of the interference in Wi-Fi comes from Wi-Fi. If I haven't said it before, I'm saying it today. Let me say that again. Most of the interference in Wi-Fi comes from Wi-Fi. Watch. If I hear somebody at neg 62 or stronger, that is non-Wi-Fi traffic, just energy from other devices or whatever it is. Neg 62 is really strong signal. Then I'll stop. I mean, if I hear somebody at neg 65, I'm still going to send data on top of it. Okay? If it's energy, but if it's neg 60, really strong. But watch. If it's somebody that is talking Wi-Fi and I can hear him, this is 20 dB lower, meaning 100 times quieter, almost whispering. If I can hear somebody talking really quiet, I still will stop. So, Anton, if it is non-Wi-Fi traffic, can be really loud, I'm still going to talk on top of it. Of course, if it's neg 62 or stronger, then I won't, because it's too loud. But if it's like neg 65 and it's non-Wi-Fi, I'm still going to send my waves. But when it's Wi-Fi devices and I can hear him like at neg 82, I'll stop. So Wi-Fi traffic is more sensitive to other Wi-Fi traffic. Does that make sense? If I hear somebody in Wi-Fi at neg 82 or stronger, or again, some documents show it at neg 85, some will show it at neg 86 or stronger, then I'll stop if they are in the same channel. And here's when we do surveys and we try to find interferers, like other devices talking in the same channel. And then I've done surveys and I say, oh yeah, this network, called the Hilton. Oh yeah, don't worry about it because that's the Hilton hotel that is, half a block down the street. No, I worry about it because they are in the same channel as we, and I can hear them at neg 78, neg 80. Oh no, don't worry about it. That's another network. If they are in the same channel, I'm respecting them. See, if you start talking Russian right now, and I don't understand what you're saying, but you're using the medium, you're generating these waves, I'll stop. And I'll wait until you stop sending you waves for me to send my waves. Of course, we're not talking English and Russian here. I'm talking a Wi-Fi network that is my company and another Wi-Fi network that is another company, but those waves, if they're on the same channel and I can hear them at neg 82 or stronger. Remember yesterday or the day before when we talked about antennas? That we showed that, hey, I'm on this building and I have this access point by the window. This guy is sending waves, and if those waves go all the way out there, not only they can be heard and decoded and they can listen to what we're saying, since I can hear over there, I am not going to send my waves if I hear somebody else talking at neg 82 or stronger. That's why the rule for the antennas says, get the antenna that covers what you want to cover without covering what you don't want to cover. I don't want to send waves and I don't want to be listening over there because I will only send waves when nobody else is talking, when there's no energy in the channel, when nav is equal 0, when I weigh my waves and when I play the game and get to 0, and when all those conditions meet, then I get to send my waves. And if I have access point here by the window and I'm listening on channel 36, everybody out there, I will only send waves when I don't hear anybody else sending waves. Questions, comments, insults? No?
Just another question or tip actually. So we are talking about physical or energy detection in continuous mode, right? So before we start transmitting, we do assess the media.
Everything.
So I mean that, okay, at a time equal to 0, we sensed the medium. We saw that the medium is free. We started the game. And when the game was done, so we run into 0 by the gate, and there's some energy, then we defer.
Yes, again. I mean, it's a miracle.
But this means, does I keep my place in queue to talk?
Yeah.
When I detect the different energy on a medium?
Yes. Yeah, you maintain your number. Yeah. You don't have to pull another number again. You just I got a 6, but then there's energy. It keeps counting down. But when you get to 0, I mean, and there's not, I don't know which one happens first. I think they're all happening at the same time, multiple mechanisms going on. But what I do know is that all of those have to be true for you to be able to send data in the medium. I mean, it's that complicated, but it's at the same time that simple. It's just that we're slowing it down here to human levels so we kind of comprehend how Wi-Fi gets to send data and avoid collisions. Okay. That's the IFS. That's the random backoff. That's the distributed interframe space stuff. And it happens that many years ago, I mean, just think about it. This is extremely inefficient. I mean, it takes a long time. And happens that these guys from Spectralink, You heard the phones, SpectraLink voice protocol? SpectraLink's a company-made phone. And then, of course, on the wire, we had quality of service. You have DSCP, differentiated, what is that? What that stand for? Differentiated Service Code Protocol for quality of service on cable, right? Any cabling guys here? Any guys from Ethernet?
The acronym, but I can't remember the full name.
Yeah.
Well,
so
type of service you can call it.
DSCP, yeah, those values, up to 46, and the user priorities is what they're called, user priorities. So they said, man, this Wi-Fi stuff, we have to make phones for this Wi-Fi stuff, but we're voice. We have voice packets to send. And we have to play this stupid game all the time. You have to pull a number, make sure nobody's talking on the channel, and then you play their game, and you get to 0, and then you send your waves. And it happens that Anton sent waves at the same time. So I fail. I have to pull another number, larger pool. And then I have to, again, make sure nobody else is talking. There's no energy in the channel. Nav is equal 0. Now I have to play the game with a bigger number. And then I have to count down to 0. When I send my voice frames, my waves that have voice, then I failed. And then I have to try again with a larger number. And it's chaos. This is not working. Our voice is all choppy because, it's not making it on time. So the stupid game is killing us. So they modified the game and they played it different. Say, okay, if we are voice and we have a SpectraLink voice, we are gonna, yes, we're gonna make sure nobody else is talking. There's no end in the channel, that nav is equal 0. And when we pull a random number, it's gonna be a number from 0 all the way to 0. And we're gonna get zeros all the time. We're going to assign zeros to our devices. And then it's my turn. It's my turn again. Oh, it's my turn again. And then, of course, they say like, but all of your SpectraLink phones are going to be bouncing against each other because everybody's getting a 0. So yeah, but I'd rather bounce against another 200-byte voice frame than bouncing with these 1,500-byte data frames. So yeah, I know we're colliding all the time, but it's just small frames, so we're going to get to a medium faster. So of course, I don't know, they most likely got sued by Cisco, or they got in trouble, basically. So like, you got to play the game as everybody else. You got to be fair. You got to play nice with everybody else, not just you getting zeros all the time. Say, but we have voice frames. We need to get them on time, or else the quality of the voice is not going to be very good. We got a problem. That's when they say like, That's why I say, you guys on the wire, you have differentiated service code protocol, the DSCP values, and you can give quality of service to voice on the wire. But in the air, we don't have that. They said, that's right. Yeah. What letter is there available on the, E. And then that's when they say like, okay, the 802.11e group, you guys get some voice people and quality of service people, really good engineers, and figure out a way to give priority to traffic in the air that has to do with voice or video, and give them some sort of priority. Does that make sense? And then they came up with this solution. EDCA, Enhanced Distributed Channel Access. So it improves the access to the channel. And how did they do that? I mean, if you have a quality of service on Wi-Fi, it's not that voice packets will go out first all the time. Like, no. It's not an absolute priority. It is a statistical priority. They said, okay, if you're a voice traffic, voice category, and they try to map it to the user priorities on DSCP, on the wire. They're not one-to-one, but they kind of try to match and say like, look, if you are voice traffic, you are going to get a different backoff number. This is arbitration interframe space number. Arbitration, like, like in football, Alejandro, el árbitro. Arbitration is that. They arbitrate, they try to give everybody a different priority. And also, if your voice, your dice that you're going to roll has only 4 positions, you're going to get a random number from 0 to 3. And if you're video, then yeah, you get the same IFs, but then you're gonna get a number from 0 through 7 every time you need to transmit. And then yes, if you are best effort or background, you're gonna get different backoff numbers, and you're gonna get different contention windows, 0 through 15. So statistically, if you're voice, you're gonna gain access to the medium more often than if you're background. Apple, I think if you're an Apple device, you're gonna have all the traffic tagged as voice. And some people say like, you're cheating. That's not, you're trying to take advantage. And they're like, no, I'm just, the protocol says then, you know, I'm just tagging all my traffic that way. I'm just playing with the system to make my traffic have a better chance of accessing the medium more often. If you have quality of service, wireless multimedia, 802.11e in Wi-Fi, this is how devices are accessing the medium. Again, it's statistical, but it is not absolute priority. But you still have a better chance to get in the medium more often. Questions up to this point?
I would add that not only Apple is playing this game, well, with its own rules. A couple of years ago, we had a session with a group of engineers. We were playing with the Wi-Fi 6. So we pulled a number of access points, different vendors, and we pulled a number of phones and laptops that support AX, and we were running iPerf either on wired network or the client devices, and we measured how many bandwidth each device gets. And basically, we found out that some vendors are still playing these games dirty, marking all of their frames as voice, thus getting more bandwidth. Even more, if you're a vendor that produces both access points and phones, you cheated for your phones as well on the access point side.
Are you talking about Huawei?
Yeah.
Okay. So that means that if you have Huawei APs and Huawei phones, you're going to get really good Wi-Fi on your phones, huh?
Right.
This will be interesting to see. Did you do packet captures and see what the priorities were on those frames?
I think the issue was that you cannot catch those frames. It's AX and there's no real tool.
Oh, you're absolutely right. Yes. Now from the AP, you probably could.
But you cannot trust it, actually. If we're talking about cheating.
Yeah. Well, some of these headers still go at legacy rate, so you could at least find the trigger frames.
So anyway, I'm not here to blame Huawei. I'm just talking about that these rules are being broken regularly. So this is not just
I mean,
one occasion.
And it is in the standard, and Apple does it too. They tag their traffic as voice, like, but this is not voice. Like, hey, shut up. You know, it's just trying to give my customers, my users, a better Wi-Fi experience. If I knew how to do that too, I'll be tagging all my traffic, and giving them all between 0 and 2 as time slots, contention windows. Okay. Ooh, is that mouse moving by itself? Not moving anything. Hey, there we go. Stay there. Okay, now move. All right. That's it for contention. I don't know time-wise, modulation. Let's just leave modulation for tomorrow. We'll do it tomorrow or another day. Unless Let me see. Yeah, let's do another time. I gotta get going with a lot of stuff in here. Gotta clean up my man cave. Saturday cleanup. All right, with this, my friends, from Argentina, Russia, Texas, and whatever else in the world you are joining us today, we have come to the end of session 343. This is part of the Wireless LAN Professionals Wi-Fi design class that comes to you 100% free and like 98% in English. Okay, I guess with that, we will save modulation for the next session. Thank you very much, guys. I know for some of you it's early, for some of you it's late, and you have beautiful weather out there in Russia. You wanna go out, enjoy with your family, your friends, walk your dog, walk your kids, walk your friends. I don't know, just go and have fun. Love for everybody and free training for everyone. Have a good weekend.
Thank
See
you.
you. Bye.
Thanks a lot.
Bye.
Thanks a lot.
Thank you.